In this lesson, we will cover implicit differentiation. The term implicit is referring to the type of equation that we will take the derivative of, an implicit equation, meaning it is not solved for y. Here I chose x squared plus y squared equals 1 as an example because it gives you a nice equation, which is the unit circle. If you could take the derivative of this equation, you could use it to analyze its graph. For example, what is the slope at this point? Or what is the slope at this point? Before this section, we've only taken derivatives of explicitly defined functions. Let's take a minute to solve this equation for y. To do that, you could start by subtracting x squared from both sides of your equation. And then to get y by itself, you could take the square root of both sides. And in doing so, you actually get two solutions, a positive and a negative solution. So there's two equations. There's y is equal to the positive square root of 1 minus x squared, as well as y is equal to the negative square root of 1 minus x squared. So over here, these equations are explicit. And that just means we have y solved for all by itself. And here, we could take the derivative of either of those equations. It would take a little bit of time, has a square root, and it's a composition. The reason that there are two solutions from this single implicit equation is because the positive square root would give you the upper half of the circle, and the negative square root gives you the lower half of the circle. I'd like to go over this new method on how to differentiate this equation because it'll be faster than taking the derivative of either of these. To explain how this will work, in example 1, I'm going to differentiate 4 different functions, and each of these should be pretty easy with the rules that we have at this point. For example, in part A, what is the derivative with respect to x of just x? And really, you can think of this as dx over dx. And if you were to cancel both of those things, it gives you 1. No surprise, the derivative of just x takes you to 1. Well, what about the derivative with respect to x of x squared? Okay, well, we have a rule for this. You bring down the 2, you copy down the x, you subtract 1 from the exponent, and you're done. I guess technically, by the chain rule, you would then multiply by the derivative of x, which is 1, but we don't need to do that. It doesn't change anything, so I won't write it. What about the derivative with respect to x of sine of x? Well, we have a rule for that too. It goes to cosine of just x, and we're done. And lastly, what is the derivative of e to the x? That is the easiest equation because it actually is its own derivative, e to the x. So where am I going with this? What if we changed the question slightly and said, well, what's the derivative with respect to x of just y? I mean, what's that equal to? Here, the answer was simply 1, but over here, the derivative with respect to y, you can think of it as like this. Well, that's actually just y prime, and that's it. To differentiate this y means you're saying, oh, we're talking about the derivative of y. And we have two symbols that we can use to represent it. Well, what about something like this? What if I said, what is the derivative with respect to x of not x squared, but y squared? Here, the same process will work. I see something squared, so I bring down the 2, copy down the y, and subtract 1 from the exponent. So I get 2y to the first. But are we done? And the answer is no. Over here, we're done because you don't have to use the chain rule. Over here, though, you do. You bring down the 2, you copy down the y, you subtract 1 from the exponent, but the chain rule says if this isn't x, you have to multiply by the derivative of y. And what's the derivative of y? It's y prime. What I just did here is implicit differentiation. We're using all of the rules that we have up to this point, but if you have something that's not x, instead it's y, you have to multiply by its derivative. Let's try that here. What about the derivative with respect to x of sine of not x, but sine of y? It'll work the same way. We take the derivative of sine, and the derivative of sine is cosine. But we ask ourselves, is this thing x? No, it's something different. The chain rule says you have to multiply by the derivative of this thing. What's the derivative of y? It's y prime. And lastly, what is the derivative with respect to x of e to the y? Well, it's e to the y. But then we go back and say, well, wait a minute. If this thing was not x, if it's anything else, we have to multiply by its derivative, and its derivative is y prime. The pattern here is when you use the chain rule, it'll put a y prime at the end of your answer. You can use either y prime or dy dx to represent this derivative. We can use them interchangeably. This one's a lot faster to write, but this one is nice because it tells you which variables you are working with. All right, so let's go back to that first example. I want to find the derivative of this equation, which gives you the unit circle. I want to use implicit differentiation to find dy dx. The idea is we're going to take the derivative of both sides of this equation. If x squared plus y squared is equal to 1, it must be true that the derivative of x squared plus y squared is equal to the derivative of 1. Here we are doing the same thing to both sides of the equation. So if these are equal, well then so are these. And to take the derivative of these sides, we have rules to do so. This side's very easy. What's the derivative of 1? 1's a constant. Its derivative is 0. Now, what's the derivative of the left side? We can go through term by term and determine what they're equal to. Starting with x squared. What's the derivative of x squared with respect to x? That's kind of simple. It's just 2x. What is new is, well, what about the derivative of y squared? Well, you can bring the 2 down front. You copy down the y. But by the chain rule, you have to multiply by the derivative of y, which we're calling y prime. If we're looking to find dy dx, which is the same thing as y prime, I can take this equation and solve it for y prime. So there's no calculus at this point. We're essentially just solving an equation for this. I'll subtract 2x to the other side of my equation. I get 2y, y prime is equal to negative 2x. I can then divide both sides by 2y, which will get y prime by itself. And we have that y prime is equal to negative 2x over 2y. Or simply, y prime is equal to negative x over y. It would also be completely acceptable to say dy dx is equal to negative x over y. Those are, in fact, the same thing. One thing to note is that when you solve for y prime, there are no y primes over here. It's okay to have x, and it's certainly okay to have a y. You just don't want a derivative over here. And that is true for either of these equations. One other thought. These equations tell you the slope of this graph at any point. I'm just going to check a couple of points to see if they actually match up with these equations. Like here, this point. This is the point 0 for x and 1 for y. What is the slope at this point? If you draw a tangent line, the slope is 0. It's horizontal. If I take this information and put it into either of these formulas, I'm expecting to get 0 back as my answer. Do I? Let's see. At the point 0, 1, if I put that into y prime is equal to negative x over y, that's negative 0 over 1. And what do you know? That's, in fact, 0. This will work for every single point that we pick on the circle. Maybe just look at one more. What about here? This is the point, okay, that's negative 1 for x and 0 for y. This is a vertical line. The slope should be undefined. Will that show up if we put this into this equation? Let's see. If we look at the point, negative 1, 0, in y prime, that's equal to negative 1 over 0. Y prime is equal to, I guess, positive 1 over 0. And this is undefined. Division by 0 is not defined. And that means, well, this doesn't have a number for the slope. And it shouldn't because it is, in fact, a vertical line. So we found one place where the slope was 0. That was here. And we found one place where the slope was undefined. That was here. There are technically two other values where that happens. The slope is also 0 at 0, -1. So the slope is 0 there. And then at this point, which is the point 1, 0, the slope is also undefined. You can check this by putting those values into either of these equations. In example 3, I'd like to use implicit differentiation to solve for y prime, which means differentiate this equation. So what we're doing is, on the left, we're taking the derivative with respect to x. So we get 7x squared plus 3xy minus y squared is equal to the derivative with respect to x of 5. And here, I'll start with the left-hand side. I'm going to go through term by term taking derivatives, starting with 7x squared. Well, that one goes to 14x. And we have plus. And now we have 3xy. How do we take the derivative of this? Well, this is a product of two functions, so we have to use the product rule. And maybe as a reminder, if you take the derivative of a product, that's u prime v plus u v prime. So here I start with taking the derivative of 3x. That's 3. I then copy down y. I then add on 3x, and then take the derivative of just y, which is y prime. I now move on to minus y squared. The derivative of y squared is 2y y prime. On the other side of my equation, the derivative of 5 is simply 0. The goal is to get y prime by itself, and the calculus part of this question is done. But now we have these two y primes with different coefficients, meaning we can't combine them. What is the strategy for solving for y prime in this case? The strategy is to take anything that does not have y prime and move it to the other side of the equation. It will allow you to factor out y prime from every term on the left side of the equation. There's a lot of writing involved, but here's what we have. We have 3x y prime minus 2y y prime is equal to negative 14x minus 3y. There are no y primes, and each term over here does have a y prime. On the left side, I can now factor out y prime. What's left over? 3x minus 2y. And how does this help us solve for y prime? I can now divide this to the other side of the equation. And I have y prime is equal to negative 14x minus 3y, all divided by 3x minus 2y. And this thing here is the final answer. And I know this because, well, I have y prime by itself. Over here, I do have x's and y's, but there are no y primes. In example 4, we're again going to use implicit differentiation to solve for y prime, meaning on the left and the right, I'm going to take the derivative with respect to x. Let's see what we get. On the left side, the derivative of 4x is 4, and the derivative of 7y is 7y prime. On the other side of my equation, it's a little bit more complicated, but we have sine of x y squared, and that is a composition of two functions. To take the derivative of sine, I know it goes to cosine. Cosine of x y squared. However, by the chain rule, I have to multiply by the derivative of x y squared. And in doing so, here again, we are using the product rule, u prime v plus uv prime. Okay, we have a first and a second. So the derivative of the first is 1, and the second is y squared. I then add on the first times the derivative of the second, which is 2y y prime. The goal is to now solve this for y prime. This is different than the previous example. I have a y prime now on both sides of my equation. The process will be very similar. It's just going to basically be a lot of writing. And there's more than one way to go about solving this. I'm just going to choose the thing that occurs to me first. I want to move this part to the left side of the equation, and I can't because I have this cosine of x y squared here. I'm going to multiply it into the parentheses, removing those, allowing me to freely add or subtract things to both sides of this equation. So that means on the left, I have 4 plus 7y prime is equal to, here I'm going to multiply this into both terms and simplify. Cosine xy squared times 1y squared, I'll write that as y squared cosine xy squared. I then have plus, I'll put the 2 first, then x, then the y, then the cosine xy squared, followed by the y prime. I can now subtract this whole thing here. This does not have a y prime, so I'm going to subtract it to the other side here. I'm going to do this all in a single step. In doing so, I get the following. 7y prime minus this whole thing. That is 2xy cosine xy squared y prime. And on the other side, I did not do a thing to this, so I have y squared cosine xy squared, and I am subtracting this 4, so I get minus 4. This is perfect. Each term has a y prime. None of these has a y prime. I can factor it out from both pieces. I get y prime times 7 minus 2xy cosine xy squared. And that is still equal to y squared cosine xy squared minus 4. At this point, we're essentially done. I can divide both sides by this whole thing. It'll be in a denominator here. This is my final answer. Y squared cosine xy squared minus 4 all over 7 minus 2xy cosine xy squared. And this is it for this example. Just to get a little more variety, in example 5, again, we're solving for y prime, but I wanted to choose one where we have to use the quotient rule. That is, if you have u divided by v and you take its derivative, what's that? It's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom, v squared. So here again, I'm taking the derivative of both sides with respect to x. So this thing. Okay, this side, that's not going to be so bad. It's going to be 2 minus y prime. But here, when you take the derivative of e to something, it is its own derivative, and so you get e to that thing. However, because it is a fraction, I have to multiply by the derivative of x over y, meaning I have to use this quotient rule, which says it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom, y squared. On the right, again, we get the derivative of 2x is 2, and the derivative of y is y prime. I really don't know if there's a great way to simplify this quickly. I think what I'm going to do is multiply y squared to both sides of this equation. So this is one gigantic term. If I multiply this side by y squared, it'll cancel it here and put a y squared in both of these terms. So here, I'm going to multiply by y squared. On the left, I get e to the x over y. I'll change the parentheses a little bit, and I'll put y minus x y prime. So if I had put a y squared here, it would automatically just cancel with this. However, on the right, you get 2y squared minus y squared y prime. I want to bring this over here, and I don't want this here, meaning I want to move it to the other side. Before I can do that, I'm going to distribute this e to the x over y into both terms. So I'm going to multiply this here and here. We get y e to the x over y minus x e to the x over y y prime is equal to 2y squared minus y squared y prime. I now can freely move things from one side to the other. I'm going to leave this alone, but I'm going to add this to this side of the equation. I'll leave this alone, and I'll subtract this to the other side. I'm doing this in one step. Y squared y prime minus x e to the x y y prime is 2y squared minus y e to the x over y. We're getting close. I can factor out the y prime on the left side. So we have y prime times y squared minus x e to the x over y. And that is still equal to 2y squared minus y e to the x over y. When I divide both sides by this, I get that y prime is equal to the right side, 2y squared minus y e to the x over y, all divided by y squared minus x e to the x over y. And this thing here is the final answer. I wanted to go back to our first example where we've already done this. We've found the derivative of this equation y prime, and we saw it was equal to negative x over y. Now, what if you wanted to find not the first derivative, but the second derivative? To do so, you would just take the derivative of this equation one more time. So we'd have to take the derivative of this, which is a fraction. And just to state the quotient rule again, it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So to do this, I'm going to take the derivative of the left side. And if you take the derivative of y prime, it's y double prime, which is the second derivative. Now on the right, if you take the derivative, we have to use the quotient rule. It's minus the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And technically we've done it. We found the second derivative. There is a single issue. Here there's a y prime that appears within this side of the equation. Ideally, it'd be better if this could be expressed just in terms of x's and y's. And there's actually a simple way to do this. Y prime can be replaced with this thing. We can just simply plug it in, and all of the y primes will be gone. Let's try it out. Y double prime is equal to negative. That's y minus x, and y prime is negative x over y, all divided by y squared. And here, it's a second derivative, and there are no derivatives on this side whatsoever. I'm going to simplify it a little bit. I have a negative and a negative. Those can cancel. And this negative, it's outside the entire fraction. So we get y double prime is negative y plus, okay, this is really x squared over y, all divided by y squared. If we do not want fractions within fractions, we can multiply the top and bottom by that least common denominator, which is y. Carry that work over here. Y double prime is equal to negative, okay, we get y squared plus x squared all over y cubed. And that looks good. I mean, there are no derivatives here. It's negative this entire numerator divided by this denominator. One thing to point out is, well, we already have this relationship that x squared plus y squared is equal to 1. So this is actually the same thing as what's appearing in the numerator. You are allowed to replace x squared and y squared with 1. And this dramatically simplifies the second derivative. It's equal to negative 1 over y cubed. And that would be a completely simplified version of the second derivative. I have one final thing to say about this question, and let's just go back to that original equation, which was x squared plus y squared is 1. So far, we've been taking derivatives with respect to x. You can, in theory, differentiate with respect to any variable that you like. So let's say you're asked to find x prime. How do you go about doing that, and what does that even mean? X prime in this case means you're taking the derivative of x with respect to the other variable, which is y. So here, I want to try that with this equation. I want to differentiate this thing, not with respect to x, but with respect to y, just to see what that looks like. So what we're going to do is on the left and the right, take the derivative with respect to y. And on the left, we have just 1, and on the right, we have x squared plus y squared. The right side is very simple. The derivative is 0. Now here, which of the two is easier to differentiate if we're taking the derivative with respect to y? And the answer is y squared. You bring down the 2, copy down the y, subtract 1 from the exponent. But if you take the derivative of y with respect to y, you would just get 1. So here you get 2y, but you don't get y prime. You get 1. What's different is, what if you take the derivative of x squared with respect to y? This will be 2x, but these two variables are different. You now have to multiply by the derivative of x with respect to y. You could use this symbol or this symbol. I'll put x prime. Here, if you solve for x prime, we will subtract 2y to the other side of the equation. And then we'll divide by 2x. And we get that this is equal to negative y over x, which is the same thing as dx dy. So the takeaway here is you can differentiate with respect to any variable that you choose that appears within your equation. The process is very similar.